Hi, my name is Vadim, and I'm happy to present our paper called One-Shot Synthesis of Images and Segmentation Masks. This is a joint work of Bosch Center for Artificial Intelligence, the University of Tübingen, and the University of Bonn. Neural networks are powerful at solving various segmentation problems in computer vision. A well-known limitation of these approaches is their immense need for training data. For example, in order to train a segmentation model, a user typically needs a dataset containing thousands of images, where each image should have a pixel-wise segmentation mask. However, obtaining large-scale densely annotated data can be costly in practice. In a high-resolution image, depicting a scene with many objects of diverse classes, such as in this example, pixel-wise annotation can take tens of minutes of manual effort. This is clearly an obstacle to a large-scale database a user may want to collect. Therefore, the problem of collecting image data with dense pixel-wise annotations becomes important in many practical applications. To diminish the human effort needed to obtain diverse and precisely aligned image mask data, it has been recently proposed to use generative adversarial networks, known as GANs. GANs are commonly designed to generate images. However, the recent literature proposed to train them to generate not only images, but also their segmentation masks. After training, such models become a powerful source of new labeled data, which can be used in practical applications. To achieve high-quality and diverse image mask synthesis, existing GAN approaches require only a few provided mask annotations. This can significantly reduce the annotation cost. However, they still rely on the availability of large pre-training image datasets and cannot learn when the number of training images is limited. This is a problem because finding a compatible dataset is not always possible in practice. In fact, some practical scenarios provide only a few or even one training image. This is the case, for example, for restricted image domains, such as images of rare animal species or of unusual traffic conditions. Existing GANs cannot be applied in such image domains, which restricts their application in some practical situations, such as one-shot segmentation applications. Therefore, in this work, we aim to learn a high-fidelity, joint synthesis of images and masks having as little limitations on the data domain as possible. To this end, we propose a novel GAN training setup in which we assume availability only of a single training image and its segmentation mask. In contrast to prior work, we do not rely on any image dataset for pre-training, aiming to train our model from scratch. After training, we aim to generate diverse new images and supplement them with accurate segmentation masks. To the best of our knowledge, such a GAN training scenario is considered by us for the first time. We call the task, as well as our model, OSMIS, abbreviated from one-shot joint mask and image synthesis. Training a GAN only on a single sample is extremely challenging. In such a low data regime, GANs suffer from training instabilities and mode collapse. Here we show the performance of previous models, semantic GAN and dataset GAN, on our task. These models suffer from memorization as they cannot produce any images that are different from training data. Notably, dataset GAN also requires manual annotation of at least one generated image. Our work has three main contributions. Firstly, we introduce a new task of one-shot joint mask and image synthesis. Secondly, we introduce a new GAN model, which is for the first time capable of learning from a single image mask pair successfully, without requiring any pre-training. We compare our model with two groups of prior GAN models, single image GANs as well as image mask GAN methods. Compared to the former models, OSMIS not only offers an additional ability to generate accurate segmentation masks, but also achieves higher quality and diversity of generated images. On the other hand, in contrast to image mask models, OSMIS does not suffer from mode collapse and training instabilities. Thirdly, we demonstrate that our model can produce high-quality data augmentation of a single provided sample, which has a potential to improve the performance of one-shot segmentation applications. Our OSMIS model is inspired by a line of works on single image GANs. Given only a single image for training, single image GAN models are designed to mitigate the memorization of limited data and to generate a diverse set of new realistic images. As our baseline, we select the state-of-the-art model one-shot GAN. Given a single image, this model achieves an impressive ability to generate new compositions of the same scene. For example, it can vary the positions of foreground objects or their number, or edit the layout of backgrounds. Note how the realism of images is preserved. The architecture of one-shot GAN consists of a generator and a discriminator, designed as a two-branch structure. In this discriminator, an input image is first processed by a low-level discriminator to learn low-level image details, such as colors and textures, and to build an image representation. This representation is next passed to two separate discriminators. The content discriminator receives the feature representation squeezed along spatial dimensions, which makes it insensitive to the changes in locations of objects. The layout discriminator, on the other hand, receives the representation squeezed along the channel dimensions, and thus evaluates the given image according to its high-level spatial layout. The final loss of one-shot GAN discriminator is the sum of losses for the low-level, content, and layout discriminators. In contrast to one-shot image synthesis, we assume that the single training image is provided with its pixel-level mask of objects, which we aim to incorporate to the training process. To this end, we introduce modifications to the baseline generator and discriminator architectures, which will be described in detail next. Firstly, we modify the architecture of the generator, enabling the synthesis of segmentation masks via an additional mask synthesis branch. We hypothesize that during training, the generator should be able to learn discriminative features that describe which objects are generated at which locations. Thus, while synthesizing an image, we collect feature activations after the last generator block and use them as input for the mask synthesis branch. This branch is parameterized as a simple convolution followed by a softmax activation. The result of this operation is an n-channel soft probability map where each channel corresponds to one of objects or to the background. The final discrete mask prediction is obtained via an argmax operation. However, to enable the training of the mask synthesis branch with the discriminator loss, the branch should allow backpropagation of gradients, similarly to generated images. To allow backpropagation, we develop a straight-through gradient estimator denoted mask argmax. After this operation, the generated masks are given to the discriminator in the discrete form, while the mask synthesis branch can be still trained with the gradients passing through its soft probability map. In order to provide a training signal to the generator, we propose to incorporate the learning of the image mask alignment to the objective of the content discriminator. Considering the provided segmentation mask, we can now select the image areas belonging to different objects and require the discriminator to learn their appearance separately from each other. This way, as the discriminator can compare the appearance of the area belonging to the same object in real and fake images, it encourages the generator not only to synthesize realistic objects, but also to label them correctly. To this end, we introduce a masked content attention module. It receives a downsampled segmentation mask and intermediate image feature representation and produces a set of n content vectors corresponding to the masked content representations of each object and background. Accordingly, we redesign the objective of the content discriminator. For each of the obtained object representations, our proposed object discriminator is induced to predict a correct identity of each object or background of a real image, while all the identities of fake images should be categorized as an additional fake class. In effect, the generator now needs to synthesize correct segmentation masks in order to fool the discriminator. Here you can see our visual results. Given only a single image mask pair, our model learns high quality and diverse one-shot image mask synthesis. We note a remarkable structural diversity among samples, photorealism of synthesized images, and a high quality of generated annotations. For example, OSMIS can resynthesize the provided scene with a different number of foreground objects, or different layouts of backgrounds. Another advantage of OSMIS is flexibility. It successfully deals with very different scene types, such as inside or outdoor scenes, supports masks with both sparse and dense object annotations, and handles masks with many objects or separate instances of the same semantic class. We compare the quality and diversity of generated images to the single image GAN models. Compared to these models, OSMIS not only offers an additional ability to generate segmentation masks, but also achieves higher image quality and diversity. Note that despite a potential trade-off between the quality and diversity metrics, our model outperforms prior models in both metrics by a notable margin. Next, we compare our model to prior image mask methods, dataset GAN and semantic GAN. The quantitative results demonstrate that both models suffer from mode collapse, as they are not able to score high in diversity. The visual results confirm that both models suffer from memorization and are unable to produce images that are different from training data. This is not the case for OSMIS, which produces diverse images and masks. Finally, in comparison to dataset GAN, our model does not require manual annotation of generated images during training. While enabling overall high image and mask quality, OSMIS can struggle if the training sample contains annotations of fine-grained object details. This happens because the discriminator of OSMIS uses only downsampled versions of input masks. In this ablation, we train OSMIS with different numbers of low-level discriminator blocks, corresponding to different degrees of mask downsampling. There is a trade-off between the quality of images and masks. Weaker downsampling can be harmful for image quality. Too strong downsampling, on the other hand, leads to failure to annotate small objects' details correctly. Although having this limitation, OSMIS discriminator still outperforms alternative ways to incorporate segmentation masks, such as simple concatenation to input images. Note that in this table, our mask content attention achieves highest image diversity and quality of produced segmentation masks. In this part, we demonstrate how OSMIS can be applied in practical scenarios of one-shot segmentation applications. At test time, one-shot segmentation models are required to learn a new class from a single annotated image. Under critical lack of data, such models are prone to overfitting. A natural way to mitigate this is data augmentation. As shown previously, our model OSMIS can augment the provided image mask pair with novel diverse samples. The ability of OSMIS to edit backgrounds or change locations of objects is difficult to achieve by means of standard data augmentation, such as horizontal flipping, zooming, or image rotation. Therefore, the samples produced by OSMIS have a potential to serve as useful data augmentation. We conduct experiments with two one-shot segmentation applications. The first of them is one-shot video object segmentation. At test time, this task provides a video and the segmentation mask of objects only in the first frame, while a model is required to segment all the remaining video frames. The second task is one-shot semantic image segmentation. In this task, a segmentation model is first trained on a large dataset. At test phase, the same model is given a single image mask pair, called support set. It contains an object of a previously unseen class. The model is then required to segment other samples, called query images, which contain instances of the same class. For both applications, we conduct experiments with popular segmentation models from the literature, OSWOS and STM for one-shot video object segmentation, and RePRI for one-shot semantic image segmentation. In these tables, we compare the performance of one-shot segmentation models using different data augmentation. The models were trained without any data augmentation, only standard data augmentation, only synthetic data augmentation generated by OSMIS, and both types of data augmentation combined. OSMIS yields a notable increase in segmentation performance for all the studied models across different dataset splits. We note that the effect of OSMIS generations is complementary to standard data augmentation, as the best results for all the models are observed when the two augmentation strategies are used in combination. In summary, our paper has three main contributions. We introduced a new GAN training scenario in which a model is trained only on a single image mask pair, without any pre-training. We introduced our OSMIS model, which achieves high quality and diversity of image synthesis, as well as high accuracy of generated annotations. We demonstrated how OSMIS can be successfully applied for data augmentation for two one-shot segmentation tasks. Thanks a lot for watching. For more details, please check our paper.